Hello, in this lecture, we will learn about image classification. Today, we will learn what image classification is and look at a dataset called MNIST. Then, we will learn how to implement image classification AI using Keras. Image classification refers to the task of classifying an image by attaching a certain label to an image. In general, when there is an object in an image, classifying images based on an object names is a common example of image classification. In general, if you take any deep learning course, you will learn about image classification technology. Today, we will create an image classification AI based on MNIST data. In general, if you first start learning modern AI techniques, many basic AI courses will teach you how to implement MNIST image classification AI. The MNIST database is a database of pictures with the numbers 0 through 9 written by hand. Here are some pictures of the MNIST database. Today, based on this database, we will build an image classification AI model that classifies what number the image represents when an image input comes in. As you can see in the previous image, MNIST image data are grayscale images, and the resolution of each image is very low. If you open one MNIST image file in its original resolution, you can see that the original size of the photo is very small as follows. Among digital images, an image in which one pixel is expressed as a value based on the amount of light is called a grayscale image. Digital images are made up of countless color dots. One point is called a pixel, and since the size of this point on a monitor is very small, the digital image visible to the human eye does not look like a mosaic. When we talked about pixels in the last lecture, we said that they consist of RGB values of pixels. However, in the case of a grayscale image, there are no RGB values for a single pixel. Instead, a single value representing the amount of light represents one pixel, which allows computers to store and process grayscale images. There are two ways to download MNIST data. If you search MNIST on Google or GitHub, you will find a file archive of MNIST image files in PNG or JPG format. However, since MNIST is a very well-known database, many machine learning frameworks provide MNIST data in ND-array format. In this class, we will not download MNIST image files and load them with OpenCV, but we will download and use MNIST ND-array data provided by the machine learning framework. Today, we will use Keras to download MNIST data and store it in variables. Activate the Conda virtual environment T1 created in the previous class. Since we also installed Keras in this environment last time, there is no need to install any additional packages. Create a file called MNIST classification.py and write the code on the slide. Then write print train input.shape below and run this program in the T1 environment. Then, a tuple of 3 numbers will be printed on the screen like this. This tuple indicates that there are 60,000 image data in the train input variable, and the resolution of one image is 28 by 28. And since one pixel color is a grayscale image, The color can be expressed as a single number in 28 by 28 image data. Now, let's rewrite MNIST classification.py. Enter the following code and save. Let me start explaining the code. Last time, we implemented a fully connected neural network. I explained that the fully connected layer in Keras is also called the dense layer. However, this dense layer can only receive a one-dimensional array as an input from the previous layer. However, the MNIST image we're going to input into the model consists of 28 by 28 pixels. Since color information in 1 pixel is also expressed as a single number, the image given as input to the model is two-dimensional data. Therefore, we cannot put MNIST image data directly into the dense layer. Thus, each row of two-dimensional data must be flattened into one row. The layer that converts multi-dimensional data into one-dimensional data is called the flattened layer in Keras. Let's look at the structure of the model. The model gets an MNIST image of 28 by 28 pixels. Therefore, the data input in the flattened layer of the model is converted into one-dimensional data. One-dimensional data goes into the next dense layer, and the activation functions of this layer are defined as ReLU, also called rectifier. Finally, the outputs of the rectifier function become input of 10 activation functions. And you can see that the activation function of the last layer is softmax. The softmax function is utilized as the activation function in the last layer. The softmax function always returns a value between 0 and 1, and the sum of all outputs returned by softmax function layer always equals 1. The softmax function is mainly used in multi-class classification problems, and to be precise, it is used as the last layer activation function of a neural network to classify images belonging to only one class. In the last lecture, we implemented binary classification AI, but this time we need to implement multi-class classification AI. And you can't use the sigmoid function when implementing a multi-class classification neural network. In general, when implementing a neural network, the commonly used loss function and the last layer function are determined according to the type of problem the neural network needs to solve. In the binary classification we learned last time, the sigmoid function was used as the activation function of the last layer, and a function called binary cross entropy was used as the loss function. However, in the multi-class classification neural network we will be making today, we need to use the sparse categorical cross entropy function as the loss function. Which loss function and last layer activation function to use depends on what kind of the task the neural network is doing. It is not necessary to understand these functions mathematically, but depending on the type of tasks performed by the neural network, it is good to know which loss function is used and which activation function is used in the last layer. If you forget these, you can search for them with the help of the search engine. There are two loss functions used to implement the multi-class single-label classification neural network we will create today. The two are the categorical cross-entropy function and the sparse categorical cross-entropy function. However, if you use the categorical cross-entropy function, you need to define the answer data as one hot encoding format when training the neural network. One-hot encoding is a way to represent any number with 0 or 1. It's a little different from binary, but if you look at the diagram on the screen, you can easily understand how one-hot encoding represents numbers. To use categorical cross-entropy loss function, you need to convert the answer data used when training the model to one-hot encoded data, and then train the model. If this bothers you, you can use a loss function called sparse categorical cross-entropy. By using this loss function, you can pass answer data as an argument to the fit function by preparing the answer data as an integer value. By calling the model.fit method, we can train the model we implemented. Try adding the following code to the MNIST classification.py file you wrote earlier. And when you run the program, you can see in the console that training is in progress and the loss is decreasing. By calling model.predict, we can get the inference result from the model for any input. Try adding the following code to your code file. Let's call the predict method using the test input as an argument, and get the inference result in the pres variable. When the predict method is called, the predict method returns an ND array. However, the model we implemented has 10 last activation functions. So when one image is input to the model returns 10 numbers. However, our goal is to know which number is written on which image. Fortunately, the index of the highest number among 10 numbers in the return value ND array of the model is the number information we're looking for. Therefore, it is necessary to find out at which index the highest number exists in the returned ND array, and NumPy provides a function argmax that returns this index. Therefore, if you put the return value of the model.predict into the argmax function, you can check the inference result of the model with the return value of argmax. You'll want to check what class the model thinks of when it receives an image input. To do this, we will print the model's inference result and the input image to the screen. The print result and show image function shown on the slide receives the test image, the model's inference result, and the index value that specifies which test image to print. And this function prints the inference result of the model as a number to the console, and also shows the test image input in a new window. When test input is passed to the model, model.predict returns preds. Among them, pres index contains the inference information of the test image that exists in the index position of test input. Pres index consists of 10 numbers. The index of the largest number among these 10 numbers is the class value you want to find. This function received this value in result variable. We will also utilize the imShow function to compare the model's inference result with the input image. The ND array that exists in the index position of pred is the value returned when the image that exists in the index of test input is put into the model. Therefore, if we compare the value of the result variable with the image at the index position of test input, we will be able to check whether the model has classified the image properly. However, as I explained earlier, since the MNIST images are very small, the images displayed on the screen will be very small. Now, write all the code you have written so far in MNIST classification.py and run the program again. The code file can also be found on the course page. When you run the program in the terminal, the inference starts after the model training, and print result and show image is called 5 times. Each time an image appears on the screen, Compare the image with the value printed on the console. And when you press any key on the keyboard, the next number is displayed on the screen, and you can check on the console which number the model predicted of the next number image. After the program is finished, we can verify that the model correctly classifies the test images. So far, we have learned how to check the output of a model. However, if the test data is very large, it will be very inefficient to compare the results with the human eye. To solve this problem, Keras provides the method model.evaluate, which evaluates the accuracy of a model. The performance of the classifier can be expressed as accuracy, and the performance evaluation of the model is performed by comparing the model's inference results with the correct answer. Therefore, when calling evaluate method, input data and answer data pairs are required for the evaluation. If you want to check the accuracy of the model, you can call the evaluate method as follows. The model.evaluate function returns the loss and accuracy of the model as a list. Add this code to the end of the MNIST classification.py program and run the program. After training, the model's performance is evaluated based on test input. At the end of the program, we can see that the model's accuracy is about 94.959% based on the entire test data. Keras is very intuitive and easier than TensorFlow 1. Eventually, the TensorFlow community integrated Keras into TensorFlow 2 while creating TensorFlow 2. Now, let's see how the Keras code we wrote earlier is different in TensorFlow 2. First, deactivate the currently active virtual environment T1, and let's install TensorFlow 2 in the new environment. Create a new Conda virtual environment T2, activate it, and install TensorFlow 2 as follows. And run the following code in that environment. This code is also available on the course page. If you check the code, you can see that the import method of MNIST classification.py written in TensorFlow 2 is different from the Keras code. This is end of today's lecture. Next time, we will learn more about image classification.